Thank you, sir. Thank you for nice presentation, introduction. And at the outset, let me thank organizers of this Indo-French conference, Professor Roy and VM Reddy, sir, for inviting me and giving me the opportunity to present our thoughts over here. Basically, I am here to talk about what are the industry fields when it comes for energy efficiency. And from that point of view, I would like to give the background, the requirement of this energy efficiency processes, and how we can integrate these processes to make or achieve net zero program of India as well as our company. As a company, BPCL as Bharat Petroleum Corporation has embarked a journey to become net zero by 2040. So I will be covering a glimpse of that in my presentation. So my talk is like this. I'll be talking about BPCL, a quick introduction to our friends from France, and then I'll be talking about some areas wherein we look at energy efficiency improvement, like loop dewaxing, light olefin separation, alternate fuels, and then the most important thing is how do we go forward. So as a country, if you look at Honorable Prime Minister has already set a vision to become a third largest economy by 2030, and to do that we require energy. However, when you go for the energy, we have a problem of CO2 emission. BPCL now currently stands as the second largest oil marketing company in India. We are Fortune 500 company in 2023. Third largest in oil refining. We have got capacity of 35 million metric ton capacity of oil refining. And to be honest, we emit about 10,000 million metric ton of CO2 per year while doing the oil refining. So there is a need to look at energy efficiency to reduce the CO2 emissions, as well as to go for the dream what our Honorable Prime Minister is chasing, to become third largest economy of the world. As they said, we are the fifth largest company in the revenue turnover point of view, and we have a capitalization of 1.5 lakh crore in last February 2024. We are recipient of Company of the Year by FIPI, and we have Mark Mass status conferred by Government of India in 2017. And we are now looking into going for net zero with embracing the sustainable solution options. Just for more grants, we have presence in upstream, we have presence in refining, we have presence in marketing, we have presence in product distribution, and to the customer access. With this already in hand, we are now looking into becoming a net zero, or looking into various domains wherein we can look into biofuels, alternate energy, solar, wind, and yet to strive to become a net zero company by 2040. To do so, we have to look into various emissions, namely scope 1, scope 2, scope 3. For students who know, do you have idea about scope 1 emissions, scope 2 emissions, scope 3 emissions? If not, I'll tell that in refining area, when we do any direct utilization of energy, and emissions coming out of that, if you go for a crude distillation, crude processing, first to do crude desalting, and then followed by that, we go for distillation. That is the direct scope 1 emission coming out of that process of CO2. The auxiliaries which are used for this, utilities which are being used for these processes, CO2 emission comes from that called scope 2 emissions, which are within our boundaries. However, when we go for the product distribution to the customers, like vehicles, we are fueling vehicles with MS and diesel, those emissions are related to scope 3, which are not a part of our emissions, but it becomes part of the customer side. However, to make that emissions neutralized, we are going for biofuel blended fuels, so that we can make these emissions lower in scope 3 side. But coming to scope 1 and scope 2, we have to look into alternatives how we can make our process efficient and go for the reduction in CO2 emission. So with this background, I would like to say here that the typical refining configuration what we have, and we use number of catalysts in the entire process of oil refining and petrochemicals. So you can find that our 90% of crude molecules see catalyst in the process, and that way we'll look at some catalysts which are more efficient in performance, so that we can have more of our throughput at the same energy control. So this is a distribution of catalysts what we a refiner use normally. If you look at overall refining area, almost 830,000 tons of catalyst per year is used across the globe. And main guzzler of the catalyst is the FCC unit, which makes MS. Followed by that is RFCC and other units are there, which have been used for making these various products from crude as well as petrochemicals. So I'll come to this catalytic dewaxing area. Today, BPCL produces about 460 TMT of lube oil by a process called catalytic lube dewaxing. Per kg of lube dewaxing, we are emitting about 1.5 to 1.8 kg of CO2. That's the number. So how do we look at reduction of CO2 during this process? How we can look at a catalyst which can help us in reducing the emissions? That's what I wanted to brief that to you and give a food for thought so that we can work collectively for this area. So if you look at the entire process, the crude which comes to refining purpose, it undergoes first the desalting process, after where we basically clean the crude. Followed by that, we go for distillation and then vacuum distillation. Bottom of vacuum distillation is called vacuum gas oil, which goes for hydrocracker to make more of diesel and distillates. And whatever left out in that bottom of the hydrocracker, that is called unconverted oil. Unconverted oil is then fed to a lube dewaxing unit to make different grades of lubes. If you look at this process, it has got two reactors. Basically, it is a first reactor is called dewaxing reactor. Second reactor is called finishing reactor. If you look at this feed of this reactor, is totally waxy. In the sense, at room temperature, it is a solid. So to make use it in a lubricant form, it has to make it in liquid form. So we have to convert that solid to liquid by using a catalytic process called dewaxing process. And followed by that, there is a finishing process because the aromatic content present in the lube oil, it has nullified. So this is a saturation process. So there are two processes are there. And then after these two processes, there are downstream process to there to look into separation of the lube oils and different product grades. So to do this process, out of two reactors, if you look at the first reactor itself is having a catalyst. Today, it is the most expensive catalyst in the refining industry. Just to give the example, the FCC catalyst what we buy, if we say it's $1 per kg, this catalyst comes to me the price of $250 per kg. It is it's noble metal catalyst, so we have to pay extra for the platinum. So see the difference of 1:250. That's the catalyst has been used in this process. It's a non-regenerable nature and with a guaranteed life of 3 to 4 years, depending on severity of operation. And it's a monopoly of licensor of ExxonMobil and Chevron. The key ingredients of this is basically a zeolite, which is tightly controlled, and this catalyst operates on a pore-mouth catalysis basis, wherein the molecule doesn't enter the pore, it reacts only on the pore mouth of the zeolite and leaves the surface of the catalyst. So while doing so now, these are zeolites which have been patented and used for this kind of catalyst. We have successfully developed this catalyst and used in our refinery ourselves. But the catalyst, what we are doing now is that it should have key features like it should have proper crystallite size, minimum VI loss during the process, low temperature operation. When you have low temperature operation, that means you are going to have low fuel fired for the getting the heat. That means I'm going to go for less amount of CO2 emission. That is the first step of reducing the CO2 for producing the lube oil. Now, how do I now go for more of reducing CO2 yet having the high productivity? That is where we are planning, we are actually working. I cannot tell more things about this because they are highly guarded areas. But what we are doing is that we are looking into a zeolite, a macro meso zeolite, which will allow us to look at high throughput of the feed under same conditions so that I can increase productivity while minimizing the CO2 emission. So this is the concept we have been working. We have been already designed the catalyst. We are going for the scale of the catalyst for replacing the catalyst in our reactor. Currently, our Mumbai refinery is using our catalyst, and this catalyst will be replaced by the new catalyst generation, the new generation catalyst. And we are trying to aim that looking into a macro meso based zeolite for loop dewaxing purpose. But what will allow is that it will have ease of transportation of heavy waxy molecules from C20 to C50, and we can get the tight control on the throughput and enhance that throughput while utilizing the same energy content. Thereby, I'm going to reduce my CO2 emissions by helping my refinery to go for curtailing the CO2 emissions while producing the lube oils. Now comes the second area what we are looking into very keenly is that C3 recovery. Why so? Because at our Kochi, we have got 3 refineries, one at Mumbai, one at Kochi, and one at Bina, Madhya Pradesh. While at Bina, we have got a propylene complex to make propylene derivatives, and we use residue upgradation technique, that is RSCC, to make propylene and form propylene in the C3 stream. The C3 stream is then separated between propane and propylene, and the challenge here is that it is highly energy intensive. Propane propylene separation is highly energy intensive. We have got before that going to that, I'll just say about what a product portfolio we have. We have got acrylic acid, and we have got series of products of propylene based, and we are marketing this product right now. Now, when it comes to this feedstock for these products, this is propylene, which comes after cracking of VGO in RFCC unit, the fluidized catalytic cracking, and we get CC stream of containing of propane and propylene. It is fed to distillation process, and the major problem is that it's cost, and second is energy consumption, very high. If you look at this energy consumption, it is 300 picojoules for separation of olefins. It's so high in the world. And if you want to reduce energy consumption for this, it has a platform to reduce CO2 conversion, CO2 emission. So what we have is that we have got a distillation column right away, presently at our Kochi refinery, to separate C3, C4 by distillation process. However, when we go for the output of the column, there is a slippage of propane and propylene. There is a slippage of propylene and propylene. So how do we now recover that? How do we separate propane from that propylene, which is already enriched in the C3 content? The problem now is that again we have to recycle the entire C3 stream, which is separated, and is giving me the problem of energy efficiency. We have got a propane propylene mixture, which is fed to the distillation column. We have got a raffinate, which is containing of pure propylene, say 85 to 90%, plus 10% propane. Or how do we get this selectively remove this propane without recycling back the entire stream? So for that, we are looking into now a membrane-based solution, wherein we can look into a hybrid matrix membrane, a polymeric zeolitic membrane, which can separate this propane-propylene either based on diffusion principle or by molecular gate effect. So these are two zeolites we have been working on it, and we have actually worked on ITQ12 system, which is basically offers a molecular gate phenomena for propane-propylene separation. If you look at propane-propylene uptake with this kind of zeolite, the challenge is that if we see that at 80 degrees centigrade, it shuts the open door for the propane. It's all silica zeolite, but it shuts the door for the propane. So we can selectively separate propane from propylene. So we want to have a membrane based on this zeolite, which will allow me a platform not to recirculate back the entire stream of C3, again enriching propylene, and effectively save the energy for separation. We are working effectively on this, but the problem what we are facing is scale up. When you go for the scale up, the challenge is the synthesis challenge is there, as well as the yield challenge is there, as well as impurity challenge. If you have formation of ZSM5 in this, the entire game is over. So we have to make all silica ITQ12 in pure form. We have been struggling, we have been doing, but we are struggling. Third option I wanted to talk about here is that dimethyl ether. This chemical, basically we are looking into energy independence. Our 85% of the energy is imported. We get it crude oil import from Middle East and other countries. To promote our Indian economy and promote energy independence, as a company, as an oil and gas sector, Minister of Petroleum and Natural Gas is promoting dimethyl ether, looking into options of how we can produce it using biomass. So I'll just give glimpse of that why it is so, because DME is basically nothing but very close to LPG. Today, if you look at our LPG consumption and demand, we are importing LPG. Almost 1 lakh crore per annum we are spending on LPG import. It's close to about $12,000 million is spent on LPG import by government of India. And it is very, very important to now reduce LPG consumption. How it is possible? Can we look into solar option? Can we look into alternative energy option? So with that in mind frame, efforts have been made. Look at the options for making dimethyl ether. Dimethyl ether, if you look at, it has got two options to make it. One is biomass gasification. We can do gasification and do syngas. Followed by syngas, we can go for direct DME synthesis for renewable. It's called RDME, it's called renewable DME. Or we can go for coal gasification and make syngas and do DME. So it has got two steps. One is direct DME we can do, that is syngas to DME or syngas to methanol and DME. The two-step process. And as I told you that it is having good characteristics as that of LPG. So it can be blended in LPG, it can be used as a LPG, or it's also having the good characteristics as that of diesel. You are looked into as an alternative for diesel for automobile. So here's a comparison. Yeah, here is a comparison. Here we have is that only problem is that cal value of DME is lower than the diesel fuel. That's the problem we have. So that going for the substitute for automobile industry may be challenging. However, it can be blended in diesel, LPG, to substitute part of LPG import by our indigenous production of fuel. If you look at worldwide scenario of DME, it is not yet picked up. It is picking up now, slowly and steadily. But if you look at, there are very few plants are there operating across the world. And if you see the growth of this industry, it is yet very, very small, almost negligible compared to the fossil fuel. And so having this background, at BPCL we are looking into production of DME process And for that thing, we are working into a direct DME synthesis process. What we felt is that it basically gives advantage in terms of higher purpose conversion of syngas. It is having low severity conditions of operation compared to two-step process of methanol to DME, syngas to DME, syngas to methanol, methanol to DME, and it can be handled at low hydrocarbon to CO ratio. So with these advantages, we have worked extensively on this area to make DME, both from syngas derived from coal or syngas derived from biomass. Here, if you look at energy equations, if you look at that, you can say that if you go for a two-step and single step is more efficient to make DME. Well, almost about there is a 30% reduction in energy savings. So there is less amount of CO2 emissions in the process of one-step process for making DME. So here are some our catalysts what we have developed at our R&D center. It is having very good selectivity for DME for direct synthesis at a conversion of about 50%. It is based on copper, magnesium, and zinc. And this catalyst has been extensively studied and already been now scaled up for going for the DME synthesis. That's our end. These are our few publications what we were allowed to publish. They are given over here. Based on this entire journey of DME development, now we are now going for a demonstration phase of our technology at a Kochi refinery, wherein we want to put up a plant of about 10 TPD capacity to produce DME from syngas. So right now we are going to use a fossil-based syngas, which is derived from petrogasification. However, our process has a full capabilities to handle syngas derived from biomass. So with this in mind, now we are going to put up a plant by June 25. That is what is the target we have. We are already on the process of setting up a plant of 10 TPD at Kochi refinery. So this will allow us a platform to reduce carbon footprint, also to look at utilization of our biomass derived syngas to make alternative fuel, which will give us a leverage to reduce our, at least to some extent, not full extent, at least for few percentage level, to reduce our crude import. But it is a baby step we have taken. But yes, we are going to take more and more steps to scale up this process further once we get the confidence of the process. So for way forward now, what we feel is strong is that there is a demand now to look at materials which can be developed so that we can have a energy efficient process. And for that, it is very, very important for us to have a very close interaction with industry academia, because the fundamental knowledge what you have and what we don't have, but we have a knowledge of scale up. So those kind of synergy has to come in. Otherwise, it will be not having any value to have such kind of workshop. So what I personally feel is that the platform is there now for us to let us leverage the platform to have a strong academic and industry collaboration to a problem which is of industrial relevance. So I again submit to all of you that look at it very carefully, and we are positive, and let us walk together. Thank you for your attention.
Long live India and France friendship.